Hello everybody. Today we are going to discuss about the role of the secondary coordination sphere in supramolecular chemistry. So we have already realized till now that different kind of metal ligand complexes have been prepared in the literature. For example, the square planar complex or the octahedral complex or the tetrahedral complex, and the primary stabilization comes from the metal ligand bonding, which involves the metal ligand which involves the overlap between the orbitals on the metal atom as well as the ligand atoms. So there is strong overlap, there is covalent bonding, but also what is important to keep in mind that this is the primary coordination sphere. Primary coordination sphere as was proposed by Warner. And Warner was the scientist who actually started this area of metal organic complexes, and he made different kind of colored complexes, and he was able to also account for the composition and later on the geometry of these complexes. But what is also important to keep in mind that the formation of these complexes is stabilized by intramolecular non-covalent interactions as well. So between the ligand backbone which is coordinated to the metal, you can also have hydrogen bonds or other non-covalent interactions which can stabilize the metal ligand complex, and the presence of these interactions beyond the primary sphere has been observed to influence the reactivity profiles of these metal ligand complexes. It influences the reactivity profiles of these metal ligand complexes, that is, these kind of non-covalent interactions which are present, and this set of intermolecular interactions which now influences the other chemical reactions which are going to happen in the presence of this metal complex is the influence of the secondary coordination sphere. So the next thing to keep in mind is that, say now you are going to have a substrate molecule which is going to interact with this metal ligand complex. So we can have a substrate molecule. Now we have the ligand, here, you have the ligand here. There can also be non-covalent interactions, NCIs, between the substrate molecule and the ligand, and based on the nature of these interactions and the strength of these interactions, it can again influence the reactivity profile of the substrate with, say, another reagent, say R, to give you the corresponding product plus Ml3, which can be coordinated by a solvent or another ligand which is present. So in this way, the presence of these non-covalent interactions which constitute the secondary sphere can influence the reaction outcomes depending upon how the stabilization of this complex takes place. So also what happens is that because of these non-covalent interactions, it can influence, as I told you, it can first of all stabilize small molecule substrates as well as reactive intermediates. So say the formation of a substrate plus a reagent gives an intermediate I, and this intermediate can be stabilized by non-covalent interactions. So stabilize small molecule substrate as well as reactive intermediates via NCIs. it can lead to an increased concentration of the substrate molecules at the primary coordination sphere PCS. It can modify the redox potential of the transition metal of interest via a peripheral change in the ligand environment. So, these are some of the changes which can take place when you actually have these non-covalent interactions which constitute the secondary sphere, the secondary coordination sphere. Also, this has got huge implications in enzyme catalysis, or when a substrate binds to the receptors in case of enzymes. So, the substrates that bind with the enzyme are already now pre-organized to give proper activation and selectivity for the reaction of interest. And we also have got redox enzymes where you can have electrons, protons and substrates. These are all the active species which participate in the transformations, and the pre-organization of the substrate allows for the facile exchange of electrons or protons between the substrate molecules and the reaction medium to allow for the organic transformations to facilitate rapid conversions, and thus they facilitate organic transformations. For example, organocatalysis is again where you have the hydrogen bonding activation on the catalyst, which then interacts with the substrate molecules in specific ways to bring about chiral induction. So, these are some of the most important attributes of the secondary coordination sphere, and so we can generalize this also by saying that you can have a metal ligand and now we can have the secondary coordination sphere, which depends upon the kind of substituents which are present. You can have a boron electron deficient Lewis acid species, you can have SO3 minus, you can have R3N plus, you can have oxide, you can have NHR, you can have crown ether appendages on this metal ligand complex. So, the kind of interactions you are going to have with these functional groups which template the primary coordination sphere will actually influence all these aspects of chemical reactions. Now, we now look at some of the most relevant examples in this regard. So, let us first look at example 1, formation of supramolecular hydrogen bonded bidentate ligands using secondary phosphine oxides. SPOs. So here we can have different examples. For example, we can consider that this one is in equilibrium with the metal phosphine. This is the, now it can coordinate, the phosphorus lone pair can coordinate with the metal ion. So this is the metal phosphine acid, and this is an example of tautomerism. And when you have got R1 equal to R2 equal to electron withdrawing group, then the reaction is driven towards the right. So you have sufficient concentration of this particular tautomer. Here phosphorus is in the 3 oxidation state, here phosphorus is in the 5 oxidation state. And the strength of this metal phosphorus bond is comparable to the metal phosphine bond as well. So how we can generate these metal complexes? Number one, the use of an external base. For example, we can have a metal in a particular oxidation state plus 2 times and 1 equivalent of the base minus the HB is removed, and we now have Mn plus coordinated with O, R1, sorry, this is coordinated with phosphorus here. So we have the coordination with phosphorus. This is the complex now. So R1 and R2. So one equivalent of the base abstracts one proton from here. So one of the ligand becomes O minus, and this the other ligand is OH. So you have this intramolecular OHO minus hydrogen bond on this metal ligand backbone. So this is the secondary coordination sphere, and we have the metal which coordinates with the phosphorus lone pair. This is the phosphorus coordination, the lone pair and the phosphorus coordinating with the metal ion. This is one way. You can all, this is when you have used an external base. You can also use an internal base. For example, you can use Mn plus X minus plus 2 R2 R1 POH. I am not writing the stereochemistry anymore, minus HX, and this X can be either OMe or OAC, and it will give rise to the this particular metal phosphine complex, phosphine acid complex. Okay. Now these kind of complexes are interesting because they can help in hydrogen activation. So these are two ways by which you can generate the active concentration of these metal phosphine acid molecules. So we can now look at SPO assisted hydrogen activation. So we now take this particular and we have now the hydrogen molecule. So it now polarizes the HH bond. So, we can activate this. Now, we form this platinum POH PPH2, this is PPH2OH, PPH2O, and we have got this hydrogen here. So, we get the platinum hydrogen bond. This is the hydride species, and this is the OH here. And now this species can be used in the hydrogenation of aldehydes. Hydrogenation of aldehydes. So, let us take one particular example where we have taken this particular, say we say this as B catalyst, 10 equivalents of acetic acid, toluene as a solvent, 40 bar pressure for hydrogen, and 95° centigrade. So, under this reaction conditions, we will get so you see that now this is the double bond which is being this is here only, and we have the alcohol. So, this is the double bond which is being reduced, the carbonyl being reduced to the corresponding alcohol. So, the conversion is 37% here, and the reagent which was proposed or the catalyst is B. So, in the presence of this catalyst, we are able to reduce the aldehyde to the corresponding primary alcohol. Modifications of these catalysts have also been used. For example, we have this. So, this is reaction 1. We can look at another reaction, cinnamaldehyde can be reduced to the corresponding alcohol as well, and so it is a chemoselective reaction because it can now selectively reduce this particular double bond and without touching this particular double bond, and this is done in the presence of a slightly modified catalyst, iridium plus 1 COD. So, we have the iridium COD here, and then we have the TBU PH O H P TBU PH. So, in the presence of this particular catalyst, and you can see in this catalyst again there is a OHO intramolecular hydrogen bond, and at room temperature 2.5 hours and only 5 bar pressure in presence of THF solvent, you will be able to get the corresponding alcohol, where we can now see that this particular double bond is untouched. The conversion rate is greater than 97% and the turnover frequency is greater than 1000. So, you can see here that such high efficiency of this processes result when we consider this kind of a catalyst which actually has got stabilization in the primary coordination sphere. Here you can see the stabilization coming. So, these kind of chemical transformations can be achieved. Another example is that you can reduce paranitro benzaldehyde to the corresponding para-nitro alcohol as well. Here also the conversion is greater than 99%. So this is one important application. We will go now to the next application of such catalyst, where the secondary coordination pair, which is hydrogen bonded, plays a very important role in transformation. We will now look at example. So we will now look at urea phos ligands. So here the design is as follows. We have a phosphorus atom. Now we have a spacer. This is the ligand design. We have the urea now, mighty, and this is R3. Now we bring in another molecule, the spacer, NHCO, NHR3, P, R1, R2. Now we know that the NHO forms hydrogen bonds. There are NHO hydrogen bonds between the urea moiety. This is something we have already studied in supramolecular chemistry. Now we can actually pre-organize, because of the dimer formation, these two spacer molecules come close to each other, and the phosphorus can now they have the lone pair of electrons, and therefore they can coordinate with the metal ion. So when they coordinate with the metal ion, now this metal can be actually palladium or rhodium, and in the presence of a metal, it will lead to the formation of this. So phosphorus will be here, phosphorus will be here. It will coordinate with the metal. We will have the R1, R2, R1, R2. Then we will have the spacer. We will have the spacer here. This is the spacer, and this is the hydrogen bond. So now you see this is the hydrogen bonding on the ligand backbone, and now you can have the metal which can coordinate with this bidentate self-assembled complex. So we call this as label it as C, and this has also been utilized in achieving organic transformations. For example, we can consider and in the presence of C, it has been observed that we get chiral center here, enantiomeric excess is 97%, and what is the exact ligand which has been used for this purpose is as follows. So we use this is the particular ligand. So this is the urea part, the urea derivative, and then we have the spacer, and then we have the phosphine backbone, the phosphorus backbone. So here R1 is equal to hydrogen, R2 is equal to methyl, and R3 is equal to phenyl. So when this is the particular catalyst, we have this particular transformation, the reduction at the double bond. Again, the reduction takes place at this particular region specifically. Now we can further modify. Now in chemistry we can modify the backbone further, and we can achieve different organic transformations, particularly chiral transformation. And so now we would like to make the backbone chiral, that is the P phosphorus chiral. So this is example 3 now. So P chiral urea phos based ligands, and its application is in the rhodium catalyzed hydrogenation of dimethyl itaconate and N-acetyl dihydrophenylalanine. So let us write down the reaction conditions, and before that we will also show you how the catalyst is made, that is P chiral urea phos. So we start with the chiral phosphorus pH O toluene group, NHCO NH2, and we add rhodium bis-cod BF4 minus, and in the presence of methyl chloride towards 0 degree centigrade, this gives rise to the this is the rhodium, and this will now coordinate with the phosphorus, which is the chiral phosphorus. NH2, this is the spacer, so here we can see there can be NHO hydrogen bonding, NHO hydrogen bonding in this particular region. So this is the hydrogen bonded backbone, and this is my chiral O toluene pH O toluene. So this is my catalyst. I can label this as now the D catalyst, which now has got the chiral backbone, which is also supported by hydrogen bonds, and we can now use this particular substrate, that is the diethyl itaconate. So this is E diethyl itaconate, and this is F. So in the presence of this is now in the presence of the catalyst D, hydrogen gas 10 bar 5 hours 0 degree centigrade, we are able to achieve the transformation and so this becomes the chiral center, and the conversion is happens and the enantiomeric excess is low, 33%. On the contrary, when we do it in the corresponding N-acetyl dihydrophenylalanine, so this is E, now this is F, then we will get the corresponding CO NH COH, this is 99% EE. And what has been recommended is that the hydrogen bonding between the urea and the substrate so the urea moiety is present in the catalyst D, and the substrate is responsible for the observed enantioselectivity. Is responsible for the observed enantioselectivity. So these are some of the important applications of the secondary coordination sphere, and the secondary coordination sphere also operates, the influence of the secondary coordination sphere also operates in biological molecules, particularly it operates in a case of enzymes, and I would like to illustrate a few examples on that as well. So first we can look at the active site of vanadium nitrogenase secondary coordination sphere. Now we have iron, sulfur, carbon, iron, and then this is fused with iron, sulfur, iron, and Fe, S, and this is the vanadium center, and there is a sulfur here which bridges these two iron centers. This is the vanadium atom sitting here, coordinated to oxygen, oxygen, CH2 CO2 minus, CH2 CO2 minus. And now between these two iron centers we have X, we have this X bridging ligand, and H, this H hydrogen bonds with this carbonyl group. This is GLN, glutamine, and this is histidine. So this is the active site. This is the active site of V-nitrogenase, and here you can see this pre-organization is important. So you have the clusters, the Cuban clusters which are fused at the carbon center. We have the vanadium active site, and we have this site which is again stabilized by hydrogen. This particular site is there, but then overall species is stabilized by hydrogen bonding between the histidine and the glutamine with the corresponding XH. So you can see that these kind of this is the secondary coordination sphere that can actually influence the reaction outcomes with these clusters. We can take another example of another active site where we can see the effect of the secondary coordination sphere in nickel iron CODH active site. So this is the carbon monoxide dehydrogenase, the CODH. and we have got here the pendant histidine and lysine that are positioned to interact with bound CO2 to lead to reduction, because you know that atmospheric carbon dioxide can now be efficiently trapped, and then reduction can be performed to form the reduced products. For example, we can form the RCO2 minus units. So this trapping of CO2 leading to the reduction of carbon dioxide can be facilitated via this carbon monoxide dehydrogenase. And at the active site we have got the histidine and the lysine. So we can look at this active site now. NH. So histidine is a wonder molecule. It is present in many applications. So you can see this is my carbon dioxide, and it is now connected to nickel. This is coordinated with iron. This is cysteine, histidine, and now this is sulfur. This is sulfur. So 2 sulfur, and then there is iron here. This is iron, this is sulfur, this is connected here, this is also connected via iron. So this is connected via iron, and this in turn is sulfur, which connects with this, and this also connects here, and then we have this particular connection here. And here the nickel is connected to cysteine. So this is the active site where you can see the nickel center, the iron, and you will see the CO2, and then there is strong hydrogen bonding which stabilizes the carbon dioxide molecule, and then this can lead to reduction of the bond CO2 group. So again you see the role of the secondary coordination sphere, which is stabilized by hydrogen bonds, and the effects of these hydrogen bonds are felt at regions which is beyond the primary coordination sphere. So I hope in this lecture I have been able to bring out the relevance of these important interactions which exist in the secondary coordination sphere and which influence the reactivity profiles. Thank you.